When a line meets a circle in a two-dimensional plane, their relationship is defined entirely by how they intersect. If the line cuts straight through the circle's boundary, crossing at exactly two distinct points, we call it a secant. Shift that line outward to perfectly graze the edge at a single coordinate, and it becomes a tangent. To see this mechanically, extend a radius from the center to that point of contact. They meet at exactly 90 degrees, always forming a perfect right angle. This perpendicular intersection gives us a strict mathematical anchor. It allows us to calculate distances and angles in otherwise complex geometric systems. Let's scale this up. Instead of a line just passing by, imagine a single point sitting completely outside the circle. From this external location, we can project exactly two tangent lines toward the curve. Because circles are perfectly symmetrical, these two tangent segments originating from the exact same external point are identical in length. We can prove this by revealing the internal structure. If we draw radii to both points of contact and connect the center to our external point, we perfectly divide this shape into two mirrored right-angled triangles. Let's put numbers to this. Suppose our active triangle has a radius of 6, and the distance from the center to the outside point is 10. How long is the tangent line? Take a moment to pause the video and use the Pythagorean theorem to find the missing length. When setting up your equation, pay close attention to the geometry. The tangent line is not the hypotenuse. The hypotenuse is always the longest side, positioned directly across from the 90-degree right angle, in this case, the line measuring 10. With the hypotenuse correctly identified, the algebra falls into place. 6 squared plus our unknown tangent squared equals 10 squared. 36 plus b squared equals 100. Subtract 36 to get 64, meaning our tangent length is exactly 8. This pattern repeats constantly in geometry. When you see external tangents, you are usually looking at a disguised right triangle algebra problem. Calculating the length is one thing, but how do we physically draw this perfect tangent line from an external point without relying on given measurements? We start by connecting the outside point directly to the circle center. Next, using a compass, we find the exact mathematical midpoint of that connecting line. This midpoint becomes the center of a new secondary circle. By drawing it this way, the original line connecting our centers becomes the diameter of this new circle. We use the points where these circles cross because of a specific rule. Any angle inscribed in a semicircle is a right angle. By choosing these intersection points, we guarantee that the line from the center to the boundary meets the external line at exactly 90 degrees. We finish the construction by drawing our straight lines from the external point through those verified intersections. This mechanical process eliminates guesswork. Every arc and intersecting line is placed specifically to force that right angle relationship we rely on for every tangent. Let's map the rules. 2 intersection points make a secant. A single grazing point makes a tangent. First, tangents and radii intersect at right angles. Second, 2 tangents from an external point are equal in length. Finally, verify the right angle to identify the hypotenuse. Advanced geometry problems are solved by combining these simple, reliable rules. Grab a compass and a straight edge, and try constructing these tangents yourself on paper.